Oh, hi T4Gers. So today I'm going to go through a few exercises that I mentioned last time that I didn't do, but today we're going to do it with some Python help, and have a look at that. It just helps if you have some computational tools to check some of your work when you're doing some elementary things in basic geometric algebra. So we'll look at that today. Okay, so first of all, let's do a little recap of last time. Remember last time in the first short I was looking at the East Coast metric. I wanted to rewire my brain to do that, so that'll be the pseudoscalar there, the geometric product of the four base vectors. Some people use E1, E2, E3 for a frame basis. I usually use gamma, but when it matters, when there's a difference, I'll let you know, I guess. Okay, now this is the critical mapping. This is the Pauli matrix, or spinner. Two column vector, two components, complex entries, and that maps to the Clifford algebra or Spacetime algebra 3,1 signature, or any signature you like, I guess, using this mapping. The scalar A0 is a scalar, and the other coefficients, real numbers, the A's are real numbers, they map onto they get mapped by the pseudoscalar times the sigma. The sigma is going to be this bivector here, which is we also call a relative vector, because it's relative to choosing a time-like direction, gamma 4. It's a choice of the observer, I guess. So these are the two that I wanted to check, this one and this one, because I didn't check them last time. We'll see how far I get on that. I might not get very far because it's going to be pretty slow going, just a steady pace, because I cater for mostly high school students who are, well, advanced high school students, let's say. So last time I checked this relationship here, the commutators, and then so today we'll look at the others. Okay, so let's go back to the exercise. What was it we wanted to prove? We wanted to show that in the Hilbert space, or the Pauli algebra. That sucks. I need a bigger. In the Pauli algebra, an I times the spinner, and it gets mapped onto the geometric algebra by a right multiplication by the pseudoscalar and the gamma and the sigma 3. All right, now let's see how that works in Python. So to start up, like I said, even though this is episode 2 of my shorts, it's not going to be a short video, as you'll see, because I'm going to have to do a few basic steps. But this is for students. So the package I'll use is called G Algebra. Shouldn't take too long to install, I don't think. So I won't pause the video here. I need to update pip, but I got the package, I think. Must have been already installed. Sorry. So I'm just doing this from the dumb old bash terminal here, and I'll just be copying and pasting some code that I had just on hand here. I'll go through it with you. So first of all, well, let's see if I can increase that a bit so you can see it better. So the first is just importing the symbols from Python, the symbolic algebra library. That's just useful for doing symbolic stuff. It's not geometric algebra. Geometric algebra import is, I'm going to alias to capital GA, and I guess I'm not going to be doing any LaTeX, but it does give you LaTeX expressions, and that can be kind of handy. All right, so let's see how this works out. So then I just put in some helper functions. You don't have to use these if you don't want to. It's just that in SymPy, the real and imaginary part get returned as a list, and so I just want to pick out the two parts, real and imaginary part. Like I said, this is going to be slow because. So then I defined some symbols that I can use. These are just going to be symbolic variables, real variables, real equals true. I could have made them complex, but I want to make all my complex numbers explicit, because that's the way we check the mapping. Capital Psi is going to be the Pauli spinner, so it's 2 components, and it's got 2 complex valued components. Capital I is the, or 1J is the unit imaginary, and Simpi. Now I'm not sure if I need this next line. Do I need it? Anyway, there I've got some more Simpi symbols if I want to. I don't think I'll use them today. Now the key thing here is to find the geometric algebra, so let's showcase this one. You can name it anything you like, but I've got orthogonal 4-dimensional geometric algebra with named basis vectors x, y, z, t, and a East Coast signature, right? That's the key thing that I wanted to check today. So I needed to have these Simpi coordinates. I guess that's why I used the Simpi. I couldn't see exactly why I was using it. Now I know. All right. I must have learned that from experience, because I forgot that's what you needed to do. Basically, you just want to go on the web and read the docs for the GAlgebra package. It has all the documentation that you need. Then I'll just alias the pseudoscalar for the spacetime. So if I print that out, it's just, you can see it's just the geometric product of the basis vectors. But since they're orthogonal, it's also their outer product. They're the same thing, so it's anti-symmetric. So these are anti-symmetric basis vectors. Alright, and then I define these sigmas, which I'm just going to call S1, S2, S3 for short. Oh, what did I do there? Oh yeah, so I like to use E1, E2, E3, E4, so that's what I'll do. So it's really, I should define those first, and then I can do the S's and this one here. So those are the sigmas that we use for quantum mechanics to do spin and everything. Now, so the only one I'm going to check today is this spinor mapping. Let's go back to the sheet. I'm going to check this one, that I times the Pauli matrix, I times the Pauli spinor is the same as in geometric algebra, psi I sigma 3. And I'll show you how to check that. So, you know, obviously I've done it on paper once upon a time, but I'll show you how to do this using the GAlgebra software. So first of all, I want to define the multivector. This is the multivector that corresponds to our spinor. The spinor, remember, was Pauli spinor was that matrix, whereas the lowercase psi is our multivector. So it's got a scalar part and it's got 3 bivector parts. By the way, I could actually just show you quickly. Checking the commutation relations is really simple. So remember, that was supposed to be twice I S3, 2 times I. That's the I for the pseudoscalar. S3 should be the same as that. And as long as you don't have floats, you can normally just use a simple comparison operator. You'll see down here in my code that I've sketched that if you have floating point numbers coming into the expressions, you have to do a little bit of a more cumbersome comparison, but that's no bad problem. Now I'll just go to shortcut the geometric algebra expression. Remember what it was? It's this one here, psi I sigma 3. So if we put that in psi, that's our basic multivector corresponding to the Pauli spinor. Then the pseudoscalar, that's capital I over here, times the sigma 3. And then let's just check that that's something sensible. Right, so it looks like that's going to map to some Pauli spinor. But instead of laboriously computing it by hand, we can multiply the matrix in the from the Simpi stuff. This is now not doing geometric algebra. It's just doing. Okay. I guess I aliased the imaginary unit imaginary from Simpy. That was kind of dumb. I should use capital I for, oh, I should use J, I guess, for that one, for the unit imaginary. And then it would be, this expression should be just the unit imaginary times the Pauli spinner. Let's have a look at what that is. So you can see these two things are supposed to be comparable. These two things here. This matrix and this multi-vector. But it's a bit of a pain to check the mapping because I haven't written a Python function to check the mapping. So instead I was a little bit dumb and I just I should put these 4 lines into a function that just checks every time I want to check my mapping from the Pauli Hilbert space to the geometric algebra multivectors. Instead I just wrote this one. So here I'm using the real part. Now let's have a look at this. Let's just go through this slowly so you can see what I'm doing here. So this is going to check the scalar part of the multivector against the real part of the first entry of the Pauli matrix, right? So what we're doing here is let's copy the mapping for reference. Might be kind of useful to do. Hopefully this comes on the screen. I haven't cut it off somehow on my screen recording software. Let's put it more in the center. Alrighty, so what I'm doing here is first of all, the first check is going to be, well, you know, it's going to be checking this part here. But of course we've changed that when we multiply by I. So it'll be on the left hand side, so check 1, I guess. On the left hand side it will be the real part of I, and it's going to be the first component. So, well, how do you indicate the first component? I guess with a subscript or something. I guess 0th component if we're doing C++ or NumPy indices. So this is just psi 0, psi 1 is what I'm saying. And you could call it up and down if you wanted to. I'll just call them 0 and 1. And we're checking to see if that is going to be equal to the scalar part of psi I sigma 3. The scalar part you can do angle brackets with the 0, but that 0 is the conventional default. So if you just mean scalar part, usually you drop the 0. All right, now that translates to this expression here. I hope you'll agree. I use Simpy simplify to avoid floating point numbers, but I'll show you. Let's just see that is true. It is true. Let's just see what that is, what these two expressions are. Okay, so that's why I won't get symbolic equals if I just do an equals on these, because I think Python is going to compare those two expressions as Simpy expressions, and it could, because of the -1 times on the second one, it won't turn out true. And of course we can see that they're true. So the way to do that, to check it, is to do a simplification and do a negative. Right, so we subtract them, and that gives us a 0. And simplifying 0 is always gonna. So it's just a roundabout way of making sure we get a proper comparison, and it's going to use the fact that instead of comparing them directly, we're going to subtract one from the other, which should give us a 0. Okay, now the next part would be, I guess, the imaginary part of the first component of the Pauli wave function. So it didn't quite fit in there. Let me give myself a bit more room. Okay, now that should be true. Let's go back to our pen and paper. So check 2. would be this one here, with one of these here, the sigma 3 one. So that means on the left hand side we should have the imaginary part of I times the spin up part of the Pauli wave function should be, oh, by the way, we can let's just whoa, we got it right. It should be the bivector part of psi I sigma 3, and well, I don't know how to indicate bivector parts in this, but I guess we could use a projection operation. So it's the E1, E2 blade part of it. So it's going to be out of the bivector part, but I want to project it onto the blade, so it'll be something like psi I sigma 3. Actually, I better check this out. Dotted into the blade, E1, E2, I guess. I think that's how it goes, but I'm not sure. My linear algebra for these multivectors is really stuff. But the idea is this. The idea of this is I just want to project out this blade part. Actually, maybe that's an exercise. I should figure out what the primitive expression is for projecting onto a blade. But that's what this sort of heuristically means. We'll check that maybe later, another day. And that's what it does. Now the cool thing about G algebra package in Python is it has some of these functions built in, so they're really helpful. So we've got that expression that we created for the for this psi I sigma 3 is a multivector in object in the library, and you can just go have a look at all the things you can do with them. And I don't know where it is, but here it is. So if I scroll down, you can see I've got a couple of things I can do with the blade structure of these things. I can also, let's actually do blade representation, see what that does. I'm not sure what arguments it needs, but let's just see what it does. Oh. Yeah, so it just shows you a representation of the thing in terms of the blades. So here there's no blade, and then these other 3 blades. E, X, E, Y. That's what it does. But the main thing is, so we just wanted to check these expressions. So we're almost done for today, because there's just 2 more to go for the spin down part of the Pauli wave function. Just for students who haven't yet caught on, let's just keep doing these. So this time we want the real part of the spin down, which I'm calling psi 1. We want to check that'll be the real part will be the A2 coefficient. So on the geometric algebra side, again, I'm just going to use this idea of this as a projection onto the psi 2. Now, okay, so the sigma 2 is I sigma 2, which is the part of the multivector, is going to be, well, should we work it out? It's sigma 1, sigma 2, sigma 3, sigma 2, and we do a transposition, so it's negative sigma 1, sigma 3. And that's important because there's a minus sign there. And when you do the blade comparison in the geometric algebra package, it won't like it if you compare with the blade E3, E1. You have to somehow, it doesn't like that. So that's no good. But this will work. But to do that check, we need a negative sign. But the thing is, there's a negative on the Pauli side as well. So I'll put a negative here just for reference. So it's really E3, E1 blade, but remember there's a negative on the Pauli side, so that'll sort of, cancel out. So when we do the simple expression, there should be a negative in front of this thing here on the multivector side, but that will compare to a negative on this side, so they cancel out, and so I can still just take the difference of these two. And just to be clear, what we've got here, that is minus E1, and this is A1 like that. Okay, now remember this one, this here was had two components, and you'll see that the real part of it is this one here. So remember, that looks like it's a positive A1, but when we compare with the Pauli mapping, it's a negative, because that's the negative sign over here. So that all worked out, and then we just got one more to do, which is the last one, the imaginary component. It's also true. So there we did an E2, E3 blade projection. So basically what this blade coefficient is doing for me is basically projecting out a particular blade. And what was that in terms of the checks here? The last check that we needed to do was the imaginary part of the spin down component, and that should have been equal to the projection of psi I sigma 3 onto the E2, E3 component, E2, E3 blade. And then those all worked out. So we can tick all that off, and next time we can do one of the other checks. Maybe the next short I'll do is check that the Pauli matrix multiplication does indeed map onto the multi-vector expression given by this in the Clifford algebra. And I believe these work in the East. This is the East Coast metric, but all of this stuff works in the West Coast as well. We haven't actually hit any particular differences between these two algebras, even though, as I mentioned before, they're not isomorphic. So we'll do that next time using probably use the software. Why not? Since it's good to get used to using it. Until then, I hope you enjoyed this little short. Like and subscribe. Feel free to donate on my Ko-fi account, because I'm doing this all as an amateur in my lunchtime, unpaid, and so I appreciate any support that there is out there. Lots more to do. This is just really just covering some basics for younger students, and more advanced students or professional physicists. I will have some content for you much later, probably next year, being realistic, and hopefully it'll be really good. And I can promise that for the professional physicist, it should be quite useful, because you may not have bothered reading the textbooks on geometric algebra or space-time algebra, but what I do is going to be pretty simple stuff, and so yeah, hopefully it'll be useful for you. So look forward to that.